What's going on, Algebros? It's Mr. C here, and in this video, we're going to discuss the exponential law. So as you're seeing at the top here, it says lots of real-life phenomena can be modeled with exponential equations, such as the following: bacterial growth. For instance, mold spores on a piece of bread, as you're seeing to the left. I know, super gross, sorry about that. Population growth. All right, so population of a city, on the rise there. Radioactive decay. So maybe you're concerned about some sort of radioactive element. As you know, or are probably aware, as time goes on, those elements begin to dissipate or decay. Depreciation of a car's value. We've discussed that before. And even things such as videos on YouTube going viral. Or perhaps one of our more recent topics, the growth of an investment that receives continuous interest. So surprisingly, all of these scenarios have a particular equation uh, that we can use to model and keep track of things like population growth, bacterial growth, or um, viral videos. And the connecting equation for all this is known as the exponential law. There are a couple other names for it. The first being the law of uninhibited growth or uninhibited decay. But in either of those scenarios, the overarching idea or equation is referred to as the exponential law. So I want to talk real quick as to why we're seeing the word uninhibited um, as part of uninhibited growth and uninhibited decay. The idea there is that we are kind of in a vacuous situation in the sense that, we're assuming that something is growing um, without any sort of external um, factors which would inhibit it. For instance, if you're growing bacteria in, say, a petri dish, um, those wouldn't be able to grow to infinity, if you will. For instance, we have space restrictions, or maybe they run out of resources such as food they might need. And the same is true for some of those other examples, such as population growth. Maybe we're seeing the population of a certain city grow exponentially, but a city is only so big, so perhaps it becomes a little overpopulated for some folks living in that city, and they decide to move to a different city. All right, so that would be an example of some sort of inhibiting external factor, or even say like a video on YouTube going viral. I'm sure we've all heard of keyboard kitty. That was definitely a viral video from back in the day. But videos don't really last for so long, say on YouTube nowadays. I mean, there's such a variety, the market's saturated, and people begin to habituate. So, um, that would be an example of examples of inhibiting factors. So we're just kind of throwing all that out when we're talking about the exponential law. We're assuming that, okay, we don't really have to take into into consideration these real life restrictions, um, such as space limitations or other videos going viral that might take away some of the viewers or subscribers of, say, a different person's channel. So that's the main idea. Let me go ahead and present to you the equation, which will actually be given in function format, known as the exponential law, also known as the law of uninhibited growth or law of uninhibited decay. So the function is the following. We're going to write a of t. So function notation standing for the amount after time t has passed is equal to a sub 0, not the Mortal Kombat character, by the way. It's going to be multiplied to e, and there's going to be a power on e having the expression k times t. And believe it or not, this is the function that can model examples such as those listed above and many, many more. That said, I do want to discuss the different components of it. I already mentioned that a of t is the function notation standing for the amount after time t has passed. So if we knew a value of a sub 0, which by the way is known as an initial amount, e is the 2.7-ish number. If we knew the value of k and the number of years or months or seconds, a specific value of t, then we'd be able to predict, how much of whatever it is that we're studying, say bacteria or people representing, the population of a city, we'd be able to predict, future values. So speaking of k and t, t is time, and the nice thing about this is that time can be in any unit. It can be in seconds, minutes, hours, days, months, years. That's a little different than what we were studying back in the last section where we were talking about continuous interest and compound interest. The time there always has to be in years, but there's not as much of a restriction for the time units for the exponential law in general. And k is known as the growth or decay rate. We're going to be inspecting a growth situation if the value of k is positive, or in other words, the value of k is greater than 0, whereas we are working with a decay model or a decay scenario if the value of k is negative or simply less than 0. All right, and we'll do an example of one of those types of models in the next video. As always, feel free to let me know if you have any questions. Otherwise, I hope you enjoyed the video, and I'll see you in the next one. Thank you.